The NCLab 2020 webinar series is funded through a grant from the Institute for Museum and Library Services and provided to the Nevada State Library Archives and Public Records System. The topic of Webinar 10 is 3D Modeling, Units 3, 4, and 5. Today's webinar is on the last 3 units in 3D modeling. We covered the first 2 units, which just created basic shapes, and then started moving them around and doing things to them. And then we went through that practice on rotating and translating the objects first in 2D and 3D and learning how to make some 3D objects. So now we're going to go to Unit 3, and really we're skill building. So I'm going to open up the document on that. The one new transformation skill that you're going to learn in Unit 3 is reflection, and it's a mirror command. And if you have little kids, we call it a flip, and then formally it's called a reflection, but very commonly it's called a mirror because it behaves like a mirror. It maps points across an axis, and of course we all made those paper hearts where you fold the paper in half and you draw a line and you cut along it and open it up, and voila, you have this beautiful heart. I remember the first time I did that, I was quite excited as a child. So this is getting a little bit more technical. You're mirroring objects in 2D, which is like the heart, and 3D, which is mirroring typically around a plane. There's different ways to mirror, and of course it applies when you have an object with symmetry. So when you map the points across, they're exactly the same on one side as the other. And then in section 14 there's a bunch of puzzles, and this is a chance to use all these visual spatial reasoning skills to solve the puzzles. It's quite fun. And get the hang of whether you're seeing all these transformations, and it also helps working with a bit of precision. We'll get to that in a bit. And then finally you get to do some pretty neat things to the objects. You can scale them and split them and erase them. So now you can start creating some pretty complex models. So there's just a little snapshot of how the levels are numbered. And then in section 11, they're mostly still practicing those rotations and translations, but this time they're not just game pieces like they were at the end of Unit 2. These are a variety of 3D objects, and you're using them to complete a complex model. Like, for instance, the very first object is a whistle, and what you're doing is you're inserting the little ball inside the whistle that makes it whistle. And so here's some examples of the sports themes, and also a couple of useful commands that you learn, which one is truncated cone and the other one is an arc. And where you primarily use those in a model or in let's say you're designing hydraulic systems or anything else, is the truncated cone changes from one diameter to another. So it's a pretty useful object to have. You just tell it the starting radius and ending radius to create the truncated cone. And here's an example of a baseball bat, and the truncated cone transitions from the radius of the handle to the radius of the end of the bat. More surface area, you can hit the ball more easily. And then the arc allows you to connect straight lines with an angle and obviously a smooth transition. It's a curve. So in this case, it's just a little miniature golf course and the little border that goes around them so that the ball doesn't go flying into the other courses. And then in 12, now we're really focusing on this mirror command and looking for symmetry. So we're looking for planes and lines and planes of symmetry in objects. Lines in 2D objects in planes and 3D. So there's your heart again. And we can create an object, and then by using this mirror command, let's blow that up for a moment, we can create the second part as a copy of that part and then mirror that part. This is how it's described. The line of symmetry is formed by all points in the XY plane whose X coordinate is 0. So the line that we're reflecting it across is perpendicular to the x-axis. In this case, it happens to be the y-axis, which is the same as a line where all x values equal 0. It's worth paying a little attention to that reasoning to understand why this command is written that way. And then in 3D, now you're reflecting across a plane rather than a line. I'll just increase that again because you can see this yo-yo. You can see the basic form here. And then it's reflected across a plane perpendicular to the z-axis to form the bottom. So that's how we write it. There you have part 2 this time. Then it shows the positioning, and it's perpendicular to the z-axis. Now we can use erase to cut something away. In this case, we made a tube, but we only needed half of it. So now we just take that same objects and erase half, and now we have an object that looks like this. And then, of course, you can still move and rotate it after that into position or do all kinds of fun things with it. Rotational symmetry we worked on quite a bit in the Visual Intro to Python course using for loops. And here it's more focusing on looking for the shape that you're going to rotate, and you're still rotating it around a point. And then, of course, you can combine using all these kinds of symmetry in your design. Okay, here's an example of a puzzle. And of course, this is just a screenshot. In the puzzle itself, you can rotate this little cage around and get a feel for whether that ball is going to come through. But in the end, you might have to do a bit of number crunching to see if it does. So those puzzles are all like that. And you can often buy toys that these puzzles are based on. So if you've got a club, they can play with the puzzle physically as they do this online. Sometimes that helps them transfer that concrete understanding of 3 dimensions into a more abstract representation. Okay, 15 is fun. You get to manipulate your objects again. You're scaling them. And you're now also working with a couple more commands. You're building shells, and you're able to round corners on squares and rectangles and things like that. So there's just some sophisticated things added to your tool chest. So here you can see what a ring looks like normally. And then here it is, and it's been scaled so that the X direction is reduced to half of what it is normally. And that's what you get as a result. And then here is an example of an object that includes a shell. And just a warning, shells are a fair amount of computation. So the programs may run a little more slowly if you have a lot of these objects in your program. And in this case, the shell, the piece of the grail that is built from the shell command is bowl, and you create a spherical shell, and then you erase half of it, and then you scale it to give it a little bit different shape, and then you move it into position. So you can see by the end of this unit, you're really practicing a lot of different skills to create these objects. And then here's one more. It's the split command. That's what it does. It splits it into 2 objects. So it's a little different than erase because now you're creating 2 objects. And there's the rounded squares. So that's just adding a second parameter, and it gives the rounding radius that will create that curve. That's basically it for Unit 3. And I'm going to go through the documents, and then we'll just look at a couple of examples for all 3 of these in the course itself. So in Unit 4, you've got all that under your belt. You're going to learn a little bit about how to modify the curved surfaces, and also how to reduce what we call computational costs by specifying the number of sides. Then we get to build a spiral, which involves about 3 lines of code. And then you get to bring in your for loops again, for loops and actually lists as well. And so this helps you automate design. Design almost always has some repetition in it, and it's great to be able to use these functions to simplify your coding. Okay, so in 16, this is an important concept in 3D modeling. Curved surfaces are actually all built out of triangles. Sometimes these are put together as quadrilaterals, but typically they're just triangles, a whole bunch of them. And you can create some beautiful surfaces all out of sometimes millions of triangles. If you want something super smooth, that is a lot more data and many more triangles and a lot of computing. So if you remember what 3D looked like, say back when N64 came out, the Nintendo games, they did look like polygons. They were pretty simple, and that's because it was expensive to render them. And if you're running Mario or a little character around the game, you just can't afford to have that computer running full blast to render these shapes. So they still look very much like polygons. And then there's a few more techniques you're going to learn. So here's a great example showing this business of smoothness. This is a cone, and the default number of facets, those are quadrilaterals that are each composed of 2 triangles. To build the cone is 64. And then you can see what happens when you increase that number to 128. Your curve is smoother and the appearance is smoother. And then, of course, you can manipulate it with less sides. So here we have a cone that has 12 faces around the sides. And then, of course, you can combine it like an elbow. In this case, the cross section of the elbow is a hexagon, so that's only 6 sides. But the curve has 24 facets, so it's fairly smooth. Looks a bit like an Allen wrench or a hex wrench. So in that case, you're actually putting in a little list for each of those, because there's 2 parameters you can vary on elbow. And spheres, you can do the same thing. You've got a couple of parameters, you can modify them, and you can get a lot of interesting objects out of that. And then you have one more way to create an object, and that's from the intersection of 2 objects. And you think of a Venn diagram, the points that overlap is what you're going to get as a result. And then spirals. There's some cool models in here. Everything from DNA, double helix DNA, screw blades for a meat grinder, a nut with a thread. And if you remember back on Prism, we created a 2D shape to begin with, and then we added a height. Well, here you need a 2D shape. Like in this case, it's a rectangle. And then that's going to be repeated. What you're going to do is you're going to take that rectangle, so here it's just called R, and we want a full rotation, so that's 360 degrees, but we also give it the end height. So you can count up 1, 2, 3, 4 squares. It'll end up here, and in that spiral, we're going to rotate through 360 degrees and end up 4 spaces above. So that's basically how it works. Now you move on to Python for loops and lists to automate your designs. first of all, you do a couple of numeric loops just to make sure you remember how to do them. In this code here, we create the rectangle and we gave it a color, and then we create a list, bars, which is empty. So you have your empty list, and then you run a for loop. You start by making an object called C, and it's a copy of this rectangle, and then we're moving it based on the index and along the x direction. So of course the first index is 0, so it just creates it in place. And then the next index is going to be 1, and so forth. So it'll just create these bars until the loop is finished, and then display all the bars. And then we're going to have a little fun with this. So for example, here's the same exercise, but this time we're going to change the color each time. So we're not just creating a copy of that object and moving it, we're also changing the color. And there's some nice little expressions here where if you remember, your RGB colors range in value from 0 to 255. So this is starting as a high value for your, see, that's RG, is green, okay, and then decreasing it, and then the blue value each time is increasing every time you run the loop. So it gets less yellow and more magenta. And that first red component is a component of both yellow and magenta, so it never moves. So this is a really fun way to see how this works. And then by the end of it, you're building, this is a model of podium, a stage, I guess, and some nice circular looking steps getting up to it. And in this case, our list is repeating a shape and changing it every time. So it's changing the radius and it's changing the height. All right, and then section 20 wraps it up by just showing how you can use this automated process in all kinds of applications. So you build a little railroad, you're building a flower with many petals, you're building a double helix DNA model, and so forth. All right, like I said, we're speeding through this today because we're covering 3 units. And fortunately, Unit 5, or unfortunately, if you are eager to learn more, there's only one section in Unit 5. And this section teaches you how to draw Bezier curves, and we'll explain that in a moment. And then from the Bezier curve, you can create these rotational solid surfaces and shells. And in Visual Intro to Python, we did some of that with using a 2D trace parallel to the y-axis and then rotating it around the axis. So it's the same idea, except that your trace is a little more complicated. So the way a Bezier curve is written in our course and a lot of types of code is that the first and last point in the list fix the end points of the line. So it actually goes through those points. The other points act almost like magnets that pull the line towards them. And the first tutorial in that section explains that in more detail. But here's some code and the results. So you can see there's a list called points, and there's a 0.2 and 0, and a 0.1 and 3, and a 0.2 and 6. And the first and last point, you can see the curve goes through it. The midpoint, it never goes through that point, but it's pulled towards that point. And there's some cool looking math behind the scenes, but you don't need to know it to make these in this program. And then now you have this trace from this line, and then that's rotated around the y-axis, and it makes this shape. And from there, you can build all kinds of stuff. These are all built using those principles. And again, as we learned in Visual Intro to Python, you can create a solid, you can create a shell, a shell has a real thickness And you can 3D print it, but it's kind of expensive. So you also have a surface which you can't print. Doesn't have that dimension, but that's handy in graphics and animations where you need the speed rather than creating something that has real dimensions for printing or whatever purpose. So those are the 3 documents. And let's just take a quick peek at some of these levels. So here you can see some of the objects that are being built. And in 11, there's a whistle. Years ago, we had a workshop where we were actually building those whistles. We had a very nice printer at our disposal that would allow us to create, use different colored materials and support matrix. So we got to make some really cool working whistles. But anyway, there you can see the whistle, and this is built just using commands in PLaSM. And then if we add the ball, just let that run for a moment. Okay, now you can see that ball inside the whistle, and it's in the right spot. So we could export this as an STL file and then go print our whistle and have a functioning whistle. So all of these exercises, now the models are looking like realistic objects. I am going to go straight through to the puzzles because they're a little different. So here's that ball inside the cage. And then this is what I mean. You can kind of see, but you still can't really tell whether it's going to go through until you do a little bit of testing, measurement. Okay, here we go. So there's this scale command that I showed in the paper. This is being used to build a model of an atom. Run it. And there you see those rings stretched out, and we now have a 3D model. And again, all these things are printable. Unit 4. Okay, we did talk about, I showed you that picture of the cone modified, and this explains it in step by step, and then incorporates it into, we're building models using these principles. And as usual in the course, the model is partially built. So in this case, the poles for the TP and a plane representing the grass underneath are already in place. What you're doing now is creating the modified cone and then cutting out the entryway. So it's you don't have to do all the steps to get a very nice looking model. It helps you focus on those particular skills. And then 17 is that's our spirals, and 18 starts getting into lists, and 19 it's building more skills with the lists, and then 20 are the applications. So this is rebuilding a railway bridge. So let's go ahead. I'm going to just go plop that in there and run the code. Let's see how it turns out. Oh, okay. Oh, I see. It's just, it was the scale was so big we couldn't see it. So that's pretty neat. There's your railroad bridge, and of course, railroad involves repeated structures. The ties, there's so many ties, and they're a certain shape, and they're exactly spaced. That's what it was. It's just, oh, I see what it is. It's the step. That's why it's looking gray. So if I change that step to 10, oh, that's so much better. I can see it better now. So if you ever see that kind of grayishness, it's just because it's been stepped down to 1 instead of 10. You can there's a lot of settings in the viewer that you can adjust. And then let's just boot on over to 21. And we'll just look at that shape being created. So again, there's procedural videos and a much more detailed explanation than what I gave, and when not to use Bezier curves. And let's just go ahead, and I think I ran this already. So all right, there's our big old spool, and there's the trace. So and you can see it is generated around the y-axis, but then you can take this whole shape and you can position it using one of your transformation commands, and you can mess with it just like anything else. Just be aware, again, you can see all those faces in that. That's our computational cost again. So the programs do run a little slower when you have a lot of curved surfaces like this that require more computations. All right. Does the ball move inside the whistle? Yes, it actually does. When it's printed, the way it's printed is that you have a hard material, and then you have a material that you can dissolve out. It's called a support material. So after you take it out of the printer, you clean it. If you have a PLA printer, which is what most people have, the stuff that's the support matrix is just basically like white glue that you use in school, pretty much. So you basically just have to rinse it out, and then yeah, you have this little real sphere that's moving around inside the space in the whistle. Yes, that was a horse race to get through the rest of the course. So next week, I'm actually going to go through a brand new course. It's Python Fundamentals. And it'll be included with libraries, and if everything goes smoothly, we'll renew the contract here at the end of the month, at the end of June, I should say, and then we'll move people into that course. It's just structured a little differently than Python programming. But this is where we're getting into, okay, now you need to learn in a programming language the way you would if you're going to be programming as a programmer. So we're out of the world of games and drawings and cool little models and the very realistic world of looking at lines of code. But that's what people need to know if they're going to get a job. So one thing we're very dedicated to is, and it's something I mentioned in the very first webinar, is that we'll provide the support for your patrons. You don't have to be an expert, and man, that helps when it gets into the advanced courses. If they have questions, we'll walk them through, and we've done that already with the library patrons who've been through that final course. It's our pleasure to do that. It's neat stuff to learn. So next week we'll go through the unit 1 and 2 in Python fundamentals, aka Python programming, and then the last week after that we'll go through the second 2 units and then just have a wrap-up discussion. So hopefully people come for that, because then that's more of a Q&A on how to implement all this great stuff. See you next week, and all the webinar recordings are now in that document, and all the documents are there, including for this week. And so I'm up to date, and I should get this webinar up and in the document pretty quickly too. See you next week for Python.